System schemas help you identify interacting objects and the forces of interaction between those objects. Interacting objects are objects that touch one another, and contact forces will then be present. And any other objects that exert field forces on one another, such as gravitational fields, magnetic fields, electrostatic fields. And so therefore the objects don't actually have to directly touch. The only field force we will work with in here will be gravitational fields. Interaction forces are represented with double-headed arrows in the system schema because they act on both interacting objects. This is a visual reminder of Newton's third law. A dashed circle encloses the objects to be studied. Contents of the dashed circle are called the system, and everything else is called the environment. All arrows entering the dashed circle represent the forces acting upon the system. Any arrows entirely within the dashed circle are called internal forces and are ignored. Force diagrams, also known as free body diagrams or force maps. The system is represented abstractly as a dot. You'll superimpose a dashed XY coordinate system on the dot such that the positive x-axis, or it could be positive y-axis, is in the direction of the acceleration or possible acceleration in the case where there is no friction. All arrows, forces acting on the system are drawn such that their tail begins on the dot and point in the direction the force would accelerate the system in the absence of other forces. The vector sum of all forces, F net, will be 0 when the acceleration is 0. In such cases, we say the system is in equilibrium. Let's look at some examples. An object slides across the surface at constant speed. The system schema would show the objects that are interacting. So that would be the object itself, the surface, and the entire Earth. It would also show the forces of interaction between them. So between the entire Earth and each other object, there is a field force of gravity. And between the surface and the object, in this case, there would be a support force. We call that the normal force because it's perpendicular to the surface. Since it's sliding across at a constant speed, there must not be any friction to slow it down. So those are the only forces involved. Now we put a dotted line around the thing that we're planning on looking at. In this case, it's just the object. Notice there are two arrows entering the dashed line. That means there will be two forces acting on the system, on the object. Now the free body diagram. So we abstractly represent the system as a dot. Then we superimpose on that dot a coordinate system that would show the positive x-axis in the direction of the acceleration. Well, there isn't any acceleration here, so we could use any coordinate system we want. We're just going to use a typical coordinate system here, xy axis. Now we draw the forces acting on the system, the object in this case, so their tails are on the dot and they point in the direction of the force. So for instance, the force of gravity on the object from the Earth, notice the Fielder-Dealer notation, that again represents 1/2 of the interaction force. It's on the object from the Earth. And that would be downward. The other half of that interaction, by the way, acts on the entire Earth. That's the other head of the arrow in the system schema. Since that is unbalanced, that would cause an acceleration, but there is no acceleration here, so there must be a force that balances this out. And according to system schema, that other force would be upward, and that would be the normal force on the object from the surface. Those two forces are exactly balanced. So we would say the net force in this case is 0, the sum of the forces, because they're in opposite directions. They actually subtract from one another. This is a situation where the system is said to be in equilibrium. So why does the object continue just to keep on sliding with a constant velocity? Well, we don't really know why it just keeps doing that. It doesn't need a force to keep it doing that. We call that tendency of an object to keep doing what it's doing, either setting motionless or continuing to move in a straight line at a constant speed. We call that inertia. Let's look at another example. An object slows down as it slides across a surface. Again, the system schema would show similar things as before, but since it slows down, there would be some kind of friction force. In this case, it's a sliding friction force, also known as a kinetic friction force. Again, notice the system has, in this case, 3 arrows entering the system. That means there will be 3 forces acting on the system. The force diagram still shows the normal force and the gravitational force balanced. But now there would be one more force entering, and this will be the friction force that acts on the object, and it will be in the direction of that force. So imagine that the only force on this was the friction force. It's slowing down, so therefore the acceleration that this friction force causes must be opposing the velocity. The velocity is to the right, therefore the acceleration must be to the left, and so is the friction force. So notice the Filo-Dilo notation. This is the kinetic friction force on the object from the surface. This is an unbalanced situation. This is not an equilibrium. The net force is not 0. In this case, the net force is the kinetic friction force. Okay, the next example. A rope is attached to an object and a force is applied, but the object doesn't move. So system schema kind of looks like this. And notice now we have one additional force. There is a tension force between the system, the object, and the rope. So now when we draw a force diagram, there will be 4 forces acting on this system. So here are the 3 forces that we had before, except this time it would be a static friction force instead of a kinetic friction force. But there would be one more force that we need to have to add to this. And if it doesn't move, it must be in equilibrium. The net force must be 0. And so that other force is going to oppose it. So the tension force is along the direction of the rope to the right. So notice the Filo-Dilo notation. Tension force on the object from the rope. It is not moving, therefore it's in equilibrium. The net force is 0. Therefore, those 2 forces, the static friction force and the tension force, must balance one another, giving us a net force of 0. Next example, example 4. A rope is attached to an object and the object moves at constant speed. So this time, instead of being a static friction force, it's a kinetic friction force. But other than that, the system schema looks the same. So now our force diagram will look the same, except instead of being a static friction force, it'll be a kinetic friction force. Again, if it's moving at constant speed in a straight line, it must be a balanced situation where we say it's in equilibrium. The net force must be 0. And so all the forces cancel one another. A rope is attached to an object on a frictionless surface. So notice this, in this situation, there's no friction between the surface and the system, but there still is a normal force, and there's a gravitational force and a tension force. So eliminating the friction force from before, we have these 3 forces. This is an unbalanced situation. This is not equilibrium. That tension force will cause an acceleration in the direction of the tension force, toward the right. In this case, the net force is equal to the tension force. A rope is attached to an object on a rough surface, and the object speeds up. So if it's moving again, we must have sliding friction force because it's a rough surface. And so our force diagram looks similar to what we had before, but it says it speeds up. So that means it cannot be balanced. The tension force must be bigger than the kinetic friction force. It is not in equilibrium. Therefore, the net force would be equal to the sum of these vectors. The normal and the weight force cancel one another, but the tension and the kinetic friction force do not perfectly cancel one another. And so we would have to subtract them to figure out what the net force is. The net force will be the tension minus the kinetic friction. An object moving to the right with an attached rope slows down. So this looks similar to the last system schema. It will have 4 forces on it. But in this case, the kinetic friction force is bigger. Notice the positive x-axis now is on the other side. It's always in the direction of the acceleration, so that the net force will always be positive. Again, in this situation, it's not in equilibrium. The net force will not be 0. While the normal and the weight force cancel, the kinetic friction force and the tension force do not perfectly cancel. Therefore, the net force will be equal to the difference between the kinetic friction and the tension. So you might be looking at the picture and you see the object is moving toward the right, but it's slowing down. Somebody might ask, why is it moving to the right? Well, again, an object tends to maintain its straight line motion unless acted upon by a force. In this case, it's moving to the right, but it's being acted upon by the friction, which will slow it down. A rope is attached to an object and a force is applied at an angle to the horizontal, but the object doesn't move. This looks similar to a situation we had earlier. Again, it will be static friction since it's not moving. Again, 4 forces. For the force diagram, this time we'd have a gravity force downward. We'd have normal force upward, but notice it's not the same length as the gravitational force. That's because the tension force, which is upward and toward the right, has a vertical component. When you add the normal force and the vertical component of the tension, it will exactly balance out the gravitational force. And of course, we can't forget their static friction force here. This is another balanced situation. The x component of the tension and the static friction force exactly balance one another. The gravitational force exactly balances the sum of the normal and the y component of the tension. And so this is said to be in equilibrium because the net force is 0. A rope is attached to an object and a force is applied at an angle to the horizontal. The object moves with a constant speed. In this situation, it's similar to the last one, except now it's moving. So therefore, we'll have sliding friction, kinetic friction, instead of static friction. Our force diagram looks very similar to the last time, but instead of being static friction, it will be kinetic friction. Since it's moving in a straight line at a constant speed, it is balanced once again. We say that the net force is 0 in this situation because all the forces cancel one another, and we say it's in equilibrium. A rope is attached to an object and a force is applied at an angle to the horizontal. The surface is frictionless. In this situation, we have no friction in our system schema. And so the force diagram would look similar to the last time, except there's no friction. Again, the gravitational force exactly balances out the sum of the normal and the y component of the tension, but there's nothing left to balance out the x component of the tension, which is colored orange, which means this is not in equilibrium. The net force is not 0. In fact, the net force is equal to the x component of the tension. A rope is attached to an object and a force is applied at an angle to the horizontal. The object speeds up over a rough surface. So this is what the system schema would look like. And the force diagram would look kind of like this. If you look at this carefully, this is not balanced. The gravitational force does balance out the sum of the normal and the y component of the tension. But if you look at this, notice the x component of the tension is longer than the kinetic friction force. Therefore, this is not equilibrium. The net force is not 0. In fact, the net force is equal to the difference between the x component of the tension and the kinetic friction force. A rope is attached to an object and a force is applied at an angle to the horizontal. The object, which is moving to the right, slows down. Looks similar to the last one's system schema, but the force diagram is a little bit different this time. Notice again the positive x-axis has moved. That's because the kinetic friction force is now larger than the x component of the tension of the rope. Again, this is a situation where it's not balanced. Although the gravitational force exactly balances the sum of the normal and the y component of the tension, the x components of the tension and the friction do not balance. They don't cancel. So the net force is not zero. In fact, the net force will be the difference between the friction force and the x component of the tension. A person pushes on an object, but the object doesn't move. Notice the system schema looks a little bit different this time because now instead of a rope, we have a person pushing, but we still have four forces. So we have a gravitational force down. Our normal force is going to be much larger this time because the push is down and to the left. The y component of the push force plus the gravitational force has to exactly balance out the normal force because there's no acceleration in the y direction. Since it doesn't move, there must be one other force to balance out the x component of the push, and that would be static friction. They're exactly balanced. In this situation, all the forces end up canceling, so the net force is zero. We say that this situation is in equilibrium. Person pushes on an object and the object moves with constant speed. Looks similar to the last time, but this time instead of being kinetic friction or static friction, we have kinetic friction. The force diagram looks very similar. Again, instead of static friction becomes kinetic friction. Since all the forces cancel, the net force would be zero. Again, this would be in equilibrium. A person pushes on an object sitting on a frictionless surface. Notice there's no friction this time. There's only 3 arrows entering the system. That means only 3 forces. Again, the gravitational force and the y component of the push force exactly balances out the normal, but there is nothing to balance out the x component of the push force. That's colored orange. In fact, the net force will be equal to that orange component of the push force, which is the x component. So the net force would be equal to the x component of the push. This is not equilibrium. We will have an acceleration to the left, and that's why the positive x is towards the left. A person pushes on an object and the object accelerates across a rough surface. So in this case, we do have friction. It's kinetic friction because it's a rough surface. So we have 4 forces. And if you look at this carefully, it's not balanced. Although the gravitational force and the gravitational force summed with the y component and the push force do balance out the normal, nothing balances out the difference between the x component of the push and the friction. So if you subtract the x component of the push minus the friction, you'll get the net force. This is not equilibrium. A person pushes on an object moving to the left, but it slows down. So it looks very similar to the last one, the system schema, but the force diagram is different. Notice this time the kinetic friction force is longer than the x component of the push. Notice again the positive x-axis has moved. It's over onto the right. That's because the net force will be pointing to the right. We'll have an acceleration to the right. So somebody might ask, why is this thing moving to the left, but the acceleration is to the right? Again, an object tends to maintain its straight line motion unless acted upon by some external force. In this case, the net force, which will be the difference between the kinetic friction and the x component of the push. An object is in free fall. First of all, if it's in free fall, there is no air resistance acting on it. So the system schema only shows the object and the entire Earth acting on it through a force of gravity. Only one force. So there's only one force on the free body diagram. Notice I chose to have positive y downward. Therefore, the net force is going to be equal to the gravitational force. This is an unbalanced situation. The net force is not zero. It is not equilibrium. A falling object encounters air resistance. In this case, there are two forces acting on it, a drag force and a force of gravity. So it looks similar to the last time. We have a gravitational force, but we have to add a drag force, which is going to oppose the motion of this object. So it's going to be upward. Notice the Feeler-Dealer notation, drag force on the object from the air. This is an unbalanced situation. So the net force is going to be the difference between these two forces. It is not in equilibrium. The gravitational force minus the drag force is equal to the net force. An object is falling at terminal velocity. Terminal velocity is when an object no longer accelerates. So we still have the same system schema, but this time the force diagram will look slightly different. The drag force keeps getting bigger until eventually at terminal velocity, it's the same size as the gravitational force. In this case, we say it's in equilibrium, the net force is zero. The person holds a rope, causing the object to remain at rest. So the system schema looks a little bit more complicated here. We have a person that's holding one end of the rope, but notice that person does not touch the system. So really, that's not even really relevant to our situation. It's just the rope affecting the system and the entire Earth. So there's only two forces acting on the system. There would be a tension force up, balanced by the gravitational force down, because it's remaining at rest. In this situation, the net force is zero, therefore it's in equilibrium. A person pulls on a rope, causing the object to move at constant velocity, constant speed. Notice it doesn't say which direction it's moving. Probably in your head, you're imagining it moving up, but it could be moving downward at constant speed. It doesn't say. Our system schema looks the same. Our force diagram looks the same too. The force is exactly balanced because it's moving at constant speed. This force diagram works whether it's moving at constant speed or whether it's not moving at constant speed. It works when it's moving at constant speed upward or constant speed downward. It's in equilibrium. The net force is zero. The force is balanced. A person pulls on a rope, causing the object to speed up as it moves upward. Again, the system schema looks the same, but this time for the force diagram, since it's accelerating upward, the tension force upward is greater than the gravitational force downward. Therefore, the net force will be the difference between these two, tension minus the gravity force. It is not balanced. It is not in equilibrium. It will accelerate upward. A person pulls on a rope, causing the object to slow down as it moves downward. So the system schema looks the same, but the force diagram looks a little bit different. Notice it says it slows down as it moves downward. So the velocity vectors would be down, but it's slowing down. So the acceleration must be upward, meaning that the tension force upward must be greater than the gravitational force downward. This is not equilibrium. The net force is not zero. In fact, the net force would be the difference between the tension and the gravitational force. A person pulls on a rope, causing the object to speed up as it moves downward. Again, the system schema looks the same, but the force diagram looks different. So it's speeding up as it moves downward, which means the gravitational force has to be bigger than the tension force this time. Notice that the positive y-axis is now flipped so that the net force will be positive. It'll be the gravitational force minus the tension force. It is not in equilibrium. The net force is not zero. A person pulls on a rope, causing the object to slow down as it moves upward. Again, the system schema looks the same, but the force diagram looks different. If it's moving upward, so the velocity vectors are upward, but it's slowing down, the acceleration must be downward, meaning that the downward force, in this case gravity, must be bigger than the tension force. Since the downward force is bigger, the net force will be downward. Notice that the positive y-axis is on the bottom. So the net force will be the gravitational force minus the tension force. Again, this is not an equilibrium. The net force is not zero. It's gravity minus tension. A projectile is rising as it follows its parabolic trajectory. Again, if it's a projectile, it does not have any air resistance acting on it by definition. So it's only the Earth through the force of gravity. And so the force diagram would just show one unbalanced force. It is not in equilibrium. The net force would be equal to the gravitational force. Notice again the positive y-axis is on the bottom. A projectile is at the top of its path. In this case, again, the system schema would show just one interaction, the force of gravity. And again, the gravitational force is unbalanced. Therefore, the net force would be just simply the gravitational force. An object is suspended by a horizontal string attached to a wall and a rope attached to the ceiling. This looks like a very complicated system schema, but the truth is we only care about the string touching the system, the rope touching the system, and the earth affecting the system through this field force of gravity. But if you're thinking about the wall and you're thinking about the ceiling, you can draw them in as well, but they have no effect on the object. So looking at the system schema, we will have three forces here. So since it's not accelerating, we can use any coordinate system we choose, and I'm going to choose a typical coordinate system that you use in math. The force of gravity would be straight down. There would be a tension force from the rope that's upward on the object. So I'm calling it tension on object from rope. And there would be a tension on the object from the string that's toward the left. This has to be a balanced situation. So notice that the gravitational force balances out the y component of the tension on the object from the rope, and the tension on the object from the string exactly balances out the x component of the tension on the object from the rope. The net force is zero. This is an equilibrium. An object slides down a frictionless surface. The system schema would kind of look like this. Notice there's only two forces acting on it. Since it's accelerating downward and to the right, it's a good idea to rotate your coordinate system for this one so that the positive x-axis is in the direction of the acceleration. The force of gravity is still straight downward towards the center of the Earth. Don't make the mistake of drawing it down along the negative y-axis. That's incorrect. It's straight downward. We had to figure out what the x and y components are for the gravitational force. The y component exactly balances out the normal force, which is perpendicular to the surface. Nothing balances out the x component of the gravitational force, and therefore this is not an equilibrium because the net force will be equal to the x component of the gravitational force on the object from the Earth. An object accelerates down a rough surface. So the difference is this time now we have friction, and specifically it's kinetic friction. The force diagram looks similar to last time, but now we have kinetic friction opposing the motion down the ramp. So the kinetic friction is up along the surface of the ramp. Since it accelerates, this cannot be balanced. Although the y component of the gravitational force balances out the normal force, nothing balances out the x component of the gravitational force perfectly. In fact, the net force will be equal to the x component of the gravity force minus the friction force. An object sits motionless on a ramp. The picture is not right there. It's supposed to be motionless. So we'd have static friction that's keeping it from sliding down the ramp. Again, the picture is incorrect. It's not moving. There's only three forces acting on this object. And notice if it's motionless, it has to be perfectly balanced, which means the net force is zero, which means it's in equilibrium. The y component of the gravitational force exactly balances out the normal force. The x component of the gravitational force exactly balances out the static friction force. Thus, the net force is zero. Thus, it's in equilibrium. An object slides down the ramp at constant velocity. If it's sliding down this ramp at constant velocity, something must be preventing it from accelerating. In this case, it must be kinetic friction since it's moving. So there's three forces acting on this object. Those three forces are the normal, gravitational force, and kinetic friction force. Since it's moving at constant velocity, it must be balanced, it must be in equilibrium, the net force must be zero. The y component of the gravitational force exactly balances out the normal force, and the x component of the gravitational force exactly balances out the kinetic friction force. The net force is zero. It's in equilibrium. An object slows down as it slides up a rough ramp. So evidently somebody gave it a toss and it's sliding up this rough ramp and it's slowing down. So again, we have sliding friction, kinetic friction acting on this. And we have a support force and we have gravitational force. So it looks similar to last time, but now since it's sliding up the ramp, again, friction has to be opposing that interaction between the surfaces, has to oppose that motion between the surfaces of the sliding, and so the friction force must be down the ramp. Be careful with this one. While the y component of the gravitational force does exactly balance out the normal force, we have two things that are causing a acceleration here. We have the kinetic friction force and we have the x component of the gravity force. That's one that often is missed. Thus, the net force is really the sum of that gravitational force in the x direction and the kinetic friction force.